Welcome on the second session where we will dive into the verification of the StatiCa Detail 2D against 2 StatiCa RCS. This part will be mostly and mainly focusing on the modeling procedures, modeling strategy, how to model it in the detail actually to having the same results as I showed in the previous session. So my name is Lukáš. I work as a computational validation engineer in company ID StatiCa, and I will take you through the session. As I mentioned, this content is quite straightforward. We'll be focusing on the modeling session, modeling procedures to show you step-by-step setting and applying of the boundary condition flows. So this is the goal of this session. And but let me remind you or make some recall from the last session that we are discussing mostly the outputs from the verification, and there have been some outcomes that are quite important. That for concrete stress, we reached the level and the matching status like under the 3.7% for concrete in the top of the fibers, and for tendon stress, we reached approximately 2.9 error in between or discrepancies in between those two solutions. But there have been um, the part that's been quite up to 15% discrepancies has been exposed on the rebars, and we are discussing also the reason why that's happening, because there is like the effect that is dismissed in the StatiCa RCS because of the simplified solution. So the tension stiffening in the ultimate limit state is basically neglected, and thanks to the fact that in the StatiCa 2D detail we are considering this tension stiffening, you will be able to see like a lowering of the strains, because there is like a portion contribution of the tension ever on the average strain. So this is it leads to like a different lever arm, different neutral axis, and also like a different stresses on the reinforcement rebars. So that's been uh, it's been the reason why we just reached the 15% discrepancies in between those two solutions. But let's come back to the modeling. As I mentioned, the goal of the session is to show you how to arrange the beam like that and receive the same outputs as I introduced in the previous session. So let's go to the detail and start with the modeling procedure. So we'll be mostly like staying in the 2D solutions. We will select the blank project that we will model everything from the scratch to make it perfectly aligned and clear. Um, we'll be using it's a concrete. I will just name it prestressed beam. It will be according to the Eurocode. Concrete is C30/37, reinforcement standard grade B500B. As you can see, we can just keep the setup like that, but I think there is like a different tendon. Yeah, this one. Why 1860 S7-15.7, like this strand diameter is 15.7 millimeters, and the standard cover will be like a 40 millimeters. Okay, so this is something what we need to align, and we can move for into the 3D scene, or currently ultimately to the app. So you will be able to see the layout of the app, where here is a like a, I would say, modeling 3D scene, um, and it's completely blank because we just selected the general section actually, or we were just starting directly from the blank project to modulate everything from the ground on the top. So I need to start with the entity. Um, there is so many options that you can leverage, but we will stay by the wall assignment. You'll be also able to like apply the beam. That's perfectly fine. Those two differences are like staying just on the part that in the beam you're able to like properly define the section, for example T section, and you'll be able to see directly the stirrups that will be um, like sticking on the edges, and you will be able to see in the 3D scene this nice 3D rendering. But in the wall, so this option is basically dismissed. So um, it's not this part. It's not developed for this reasons, and you're able to just specify only the some arbitrary shape with some specified width that is like specifying the stiffness of the structure, but the stirrups will not be able to having the same shape as the beam. So the wall is quite general approach. Beam is more specifically oriented for like beams. For my purposes, I use the wall, but if I select the beam for this type of the structure, I will receive the same results. So both options are correct actually. But I will select the wall. So the width is basically 10.3 meters. The total length is like 10 meters, but once I was like specifying the 1 dB model in some global FEA, so I have some like a specifically defined boundary conditions at the end of the members, and they are at the position like 0 and 10 meters in the x on the x-axis. But actually, for this part, you will be specifying the base plate or some width of the support, and I would like to have it directly above the supports, 10 meters, and the width of the plate on the bottom edge is basically 30 millimeters from both sides. So if you are in the middle, so you need to specifically define this 10.3 millimeters distance to have it precisely 10 meters above the center of the support. So 10.3 millimeters, the height is 1.2, and the thickness is 0.0.20, 0.25. So once I will specify that, I can just move to another entity that is called boundary condition. As you can see, there is like a plenty of the boundary conditions um, that I'm able to specify. Each support is fitting to like a different discontinuity region. For this purpose, we'll utilize the point bearing support, point bearing plate. So once you specify that it's attached to the edge, you will specify the constraint or boundary condition that you will constrain, because that's a simply supported beam. So, and we are actually in the plane. So as you can see, 3 degrees of freedom, two of them are restrained, and they will specify the width that is like 0.3 millimeters, and the thickness is 50 millimeters. The thickness is important because the plate in the outputs, it's not like visible from the sense of the sense of the stresses, but it has some like a bending stiffness base, and the bending stiffness is dependent on the thickness of the plate. So once the support is like specified here, so once the plate will be more rigid, so the loads will be more equally redistributed. So I just specify the thickness 50 millimeters, and the position is 0.5 15 from the beginning, and I'm perfectly aligned. This is my 15 millimeters from the left edge, and this is my point that right now this is the center of the support. So actually, once I just copy this operation, here's a like a copy button, and I will specify it from the end and release it in the X direction, I'm able to see simply supported beam with identical supports on the left and the right side, but with the released option on the right side to consume and absorb some level of the prestressed forces. So there is a space to specify the load case. The load cases in the first stage, I will introduce you the load case types that you will. I would say I would call it steps. Yeah, because that is very important that load cases, as I mentioned here, like pre-stressing, permanent, and the variable, they have some hierarchy. So the hierarchy is coming from that if you specify the pre-stressing is like a step one, you know. Permanent is step two. Variable is step three. It has also more consequences, but actually, if you want to edit some incremental load, you will at first pre-stress it. So you will specify pre-stressing, and into the pre-stressing, once you are like a pre-stressing the structure, there is also being activated the self weight, because the self weight is working together. Once you pre-stress it, that's automatically activated. So you should include it together in the first load case that you can call pre-stressing. Okay, so once I will just create another load case that I can call um, permanent. Yeah, permanent. And the permanent stage is quite important because there is the dominant level of the load where I will specify the line load. The line load, as you can see, it's been detected on the top surfaces as a default. This is the H number 3, and the global intensity is minus 20 kilonewton per meter. Be careful once the loads is quite enormous, quite significant. There can happen that if this part of the structure is not properly reinforced, and there is some unreinforced cover that can it can basically fly away. The element can fly away, and it can lead to like a divergency in your simulation. So this is like second load case is a permanent. Right now I can utilize the option of the copying, and right here variable. Okay, I got it. uh, so that is minus 15. So at this point I have all three load cases that's I need to cluster into the combinations, because the um, solution is based on the like a combination approach, and running and introducing the or post-processing the results for the combinations. So at first I will prepare the C1 combination, and I will call it, if I rename it, so this is like a pre-stressing plus pre-stressing plus self-weight. Yeah, we'll just call it like that, self-weight. So once I have it, I will be investigating just the ultimate limit state, and I will put here 0 and 0. So this is basically my first construction stage when I pre-stressed the structure in the 28th day. So I don't need to somehow rearrange in the material properties the modulus of the elasticity, neither the strength. So it means I can copy this combination, and I will type here plus permanent. So this is my second combination where I include the permanent. As you can see, I'm just adding the partial factor one because I'm considering from the last session and from the global FEA that I just already analyzed the structure for ultimate limit state with the partial factors. So I'm using the design values. This is the reason why I'm just adding the partial factor one. Otherwise, if you are like a combining everything here, of course you need to use like a 1.35 for permanent and 1.5 times the fee for the relevant combination. But actually, this one can remain like that. Or can yeah it can you can keep it like that or you have um to have it right. Okay, perfect. So this is second combination. I can just copy the third combination where I will just rename it plus variable. Okay, this is my third and the last combination where I will insert the factor one, and as you can see, this is like this matrix showed you that this is my first load case where it's just the self weight plus permanent because it's in the one it's combined together. Self weight pre-stressing plus permanent. I just edit on the diagonal one, and I just edit also the one for the last construction stage. So that's symmetrical. Sorry, symmetrical. That's the prescription of the combination, and we can turn it into the or move on to the rebar. So at first, I will specify the pre-stressing tendons. The pre-stressing tendons um, will be exposed after you specify the pre-stressed load case. So this is my pre-stressing. So I will specify the tendon. The tendon will be type pretensioned. There will be just the one strand of the pretension tendons with a zero level of the long-term losses because I was comparing the results with the same setup, and actually right now keep it as a zero. But of course for standard use cases, once you will be like designing the structure, you will estimate your long-term losses in between the like a 10 till 20% based on the tendon properties on tendon layouts and the structure. But you should receive the best option is to receive the results coming from the time-dependent analysis. For example, if you utilized the app StatiCa beam, you're able to know and to find out what is the stress level for the tendon in the current construction stage, and insert it here once you want to, for example, add some opening into the beam. But let me come back. So the goal is to specify it like that. So the master point is W1. This is the structure. The second master point is also W1, and I will specify it from the point 1 to point 2. Or sorry, from the 8 to 6, the master point 8 to master point 6. And this is my stress. So I will specify 1100 megapascal, and also here 1100 megapascal. So if you go closer, you can see that for pretangent, the stress in the pre-stressing reinforcement just before the release from the abutments, stressed after short-term losses due to anchorage set, loss due to deformation of abutments, short-term relaxation. So just before the release. So before you like cut off the strand, actually, um, you will specify the stress here. So this is like that, and we can move to specifying of the reinforcement rebars. But as you can see right now, if I show you how it looks in the 3D rendering, you will be able to see that the tendon is directly in the center of the gravity. But we need to move it about the 450 millimeters, 450 millimeters down. Okay, the same here. And right now, that's perfectly aligned and according to the global FEA model that we had, and we were receiving the results. So I will just save it. Okay, perfect. I have it, and we can move to specification of the reinforcement results or reinforcement rebars. The part of the assembly where you're able to specify the wire fabrics, and group of the bars. All the other options that you're not able to fit in are deactivated, so you are not able to make any mistake with the specification of the bars, because you're not allowed to do that. And the group of the bars, the first group of the bars will be the horizontal bar. We need to at first change the cover, because the cover is like a 58 millimeters from the bottom. The diameter will be 16. The anchorage type at the beginning and at the end is straight, and there will be like two bars in the layer, and the number of the layers is 6 after 214 14 millimeters. It's equally redistributed over the height of the beam, and we can say that once we copy this operation, we can say that the diameter of the stirrups will be 12 millimeters. It will be related to the edge number 2. The cover is like a 40 millimeters from the edge, and there are like two bars in a layer, and there will be like a 35 bars after the distance 300 millimeters each, and that's perfectly aligned. So actually right now we have everything, but for the material properties of the tendons to having aligned with the assumptions what we have um, in the global FEA model, I will go to the material properties, and once I will go to this pre-stressing, you can see that's perfectly aligned. That's perfectly aligned. There's no need to change something. Uh, it looks really, really good. The area of the tendon and the diameter is perfectly aligned, and we can basically move to the analysis. There is coming the nonlinear analysis. Materially nonlinear analysis, where we are utilizing the for this simulation parabolic rectangular diagram for concrete with effect within the effect of the compression softening, and reinforcement rebars, where is a tangent stiffening on the bars, thanks to the portion and contribution of the like average stress in the tension. And also there is included the bond that that is where is the like nonlinear relation in between the force and the slip, or stress and the slip, that looks like quite perfectly rigid and with a big plastic elongation or permanent deformation of of the slip. Yeah, so there is like a big portion of the slip on the bars um, until you reach the exceeding of the criterias. And yeah, right now we are counting some third combination. There is prestressing sulfate Okay, so you can see we just received the results and the summary overview of all results. Where the critical combinations is the last one. So where all the increments coming from the previous construction stages are involved. So we will just go step by step. Every construction stage will be discussed and the and exposing the strain and the stresses on the concrete rebars and the tendons to verify that the results are exactly the same as in the previous session. So at first, I encourage you to always double check what is happening with your external and internal forces as a reactions. There has to be, it has to match that all, I mean, external loads has to be equal to internal loads, or mostly right now in this form the reactions, to have it equilibrium, static equilibrium. Otherwise, if you will not be equilibrium insisted here, mm, double check the model and the pre-assumptions. So at first, in the strengths, we will go to the first construction stage, where we'll display what is happening in the stresses. So you can see the critical place is not in the middle of the beam, but we will be investigating this middle section, because that's been the goal of the verification. But the critical stress under compression is close or near to the level of the support, where we can expect some discontinuity, clear discontinuity regions, where the Navier hypothesis is not valid at all, and the solution is not um, the solution that is coming from the beam. It's not basically capturing those effects in these discontinuity regions. So we will be solving the area here. So I would like to see what is happening under compression. So you can see minus 0.8 megapascal for the second construction stage. It will be increased to 7.4, and in the last construction stage there should be 12 point show here 12.9 megapascal. So you're able to see how the curvature is changing here based on the adding of the stresses, or adding of the loads. Prestressing permanent variable, all three pillars, and you can see the stresses. Okay, so that's basically for stress in the under compression. We can move to the reinforcement itself. So once I will just come here, uh, see what is happening on the rebars in the middle. There is a 2.6 megapascal under compression, so it means in the first construction stage the section is fully compressed. In the second combination, or second construction stage, we can say that there is like 178.6 megapascal. It is the increment more than the 180 megapascal. And in the third last construction stage, thanks to the another increment of the loads, we are on the 366 megapascal. So this is the final value of the stresses that is on the reinforcement bars, and we can move on to the tendons. So on the tendon, we are expecting there is really nicely visualized how the anchoring the anchoring stresses is developing over the length of the rebar, because at the beginning there's how the tendon is basically um, embedded and nested inside the concrete volume, or concrete uh, grains, and in general the mixture. So there is uh, there is the increasing of the stresses, linear increasing of the stresses, and at this point, the tendon is fully anchored. the stress from this transition zone is increasing linearly. So this is the assumption that is coming from the code. But our goal is to having the code check in the middle of the beam where all those effects as the transmission length is far away, so because that's fully anchored here. So I will show you the chart that's here. We can add another um, increment, another construction stage, and we are achieving the stress levels 1205 megapascal, and in the third construction stage we are in the 1372 megapascal. So this is the limit or the maximal value in the tendon, and we are actually on the 86.1% of the utilization. You're able to see because your sigma p limit will be somewhere around the 1450, I think, so something like that, and we are reaching 86% of the utilization. So once we come back to the deformation, always check the deformation. So this is like a first construction stage. You can see it's total deformation, and the deflection in the middle is quite 0.2 millimeters, is quite low. If I add another increment, so I'm on the 9 millimeters, and in the last construction stage for ultimate limit state. I know that this is not a goal to check the deformation for ultimate limit state, but I would like to point it out that here you're able to visualize it. Okay, and this is it basically. You're able to generate a report, but this is not the goal. So let me come back here to presentation. Um, so I've been endorsed as a certified trainer. So if you want to have a consultation on your project and or training for your company, just do not hesitate and contact me on the Struck Insight at gmail.com or on my LinkedIn profile, where I'm quite active, so I'm posting everything what is happening, or most of the like events and um, like a development what is happening in the idea StatiCa. So feel free to follow me here, and thank you for the attention of this session.